Hello guys, so in this video we are going to see the numerical based on the cooling load estimation. So basically the cooling load estimation is nothing but to find out the capacity of the room for which the air conditioner is required, or it is nothing but the what capacity air conditioner is to be put in that particular room to maintain the room at a required condition. Fine. So that is the cooling load estimation. So here is the statement given. So an air conditioning is designed for a room when following data is available. Outside conditions are given 35 C dBT and 26 C WPT. Room conditions are given as 27 C dBT and 55% RH. Heat flow through wall, roof and floor, it is given as 6.2 kilowatt. Solar heat gain through glass is given as 2 kilowatt. Equipment load is given as 2.9 kilowatt. Infiltration load is given as 400 meter cube per hour. Total number of occupants are given as 50. Sensible heat per person as 58 watt. Latent heat per person as 44 watt. Product sensible load is given as 0.2 kilowatt. Apparatus dependent temperature is given. It is 8 degrees Celsius. It is 8 degree, not minus 8. Okay, and the 80% of room air is recirculated and mixed with the 20% of fresh air. We are supposed to evaluate the room sensible heat factor, then the supplier condition, bypass factor, and the cooling coil capacity in terms of refrigeration. Fine. So this is what the statement given. Such type of statement you'll be having. In some of the cases, they may give that only solar heat gain through glass they will give, or solar heat gain through wall, roof, floor, glass, everything they will combine. They may not be giving you the equipment load. Okay, they may not be giving you the occupants load. Likewise, so that changes will be done in the statements. But whatever procedure I'm going to explain you right now, the same procedure you are going to follow for such type of problems. Now, in this numerical, if you see the room sensibility and room latent heat is not given directly, which was given in the previous case. So in the previous problems, we were having the room sensibility and room latent heat given directly, so we can easily use to get the room sensible heat factor. Here that is not the case. So you are supposed to find out what is the total room sensible heat, total room latent heat, and from that you will be getting the RSHF. And for that thing, you need to identify which are the components are contributing to the sensible heat, which are the components are contributing to the latent heat. So first thing, RSHF we will go. So first we will find the room sensible heat room sensible heat over there. Okay, so fine, I will just go on finding the step 1, or the first step. I'll find RSHF. To get the RSHF, we know that the RSHF is equal to RSH upon RSH plus RLH. Okay, this is the formula. Now RSH, that is room sensible heat. Room sensible heat. So here we need to understand what are the factors which will come under the room sensible heat, or what are the factors will be adding the sensible heat to the room. Okay, so fine, these things are okay, outside and inside conditions. Heat flow through wall, roof and floor. So this we know, this comes under the sensible heat only. Solar heat gain through glass, again this is the sensible heat only. Equipment load, again it is only sensible heat. Yes, infiltration load, it will be sensible heat plus latent heat, both it will come. Total number of occupants are given, okay, 50. So this is sensible and latent both. Okay, this is, and you can see, so sensible heat per person, latent heat per person is given. So from this also you can identify for occupants it will be sensible and latent. Product load, it is the sensible heat directly given. Okay, so if I want to calculate the sensible heat, I need to add heat flow through wall, roof, floor, then this particular solar heat gain through glass, equipment load, occupant sensible load, then infiltration sensible load, occupant sensible load, and the product load. So finally I'll have the formula room sensible heat is equal to, that is solar heat gain, or the heat flow, solar heat gain through wall, roof and floor plus solar heat through solar heat gain through glass, okay, plus, okay, we'll go back. So this is over. I have considered this, I have considered this. Equipment load, fine. Then I will write the equipment load. Then obviously you need to write down the first formula, then you just put the values. Then have the infiltration. In infiltration you have the sensible as well as latent. So infiltration load, it will be infiltration sensible heat, fine. Then then you will have occupant sensible load. Okay, so this is what I'll write: occupants sensible load, sensible heat, plus you'll have the, so here the sensible heat per person is given, so that you will be having, and then you'll have the product load, which is again a case of sensible heat, so it's a product load. Okay, so this is the formula for room sensible heat. So we will calculate one by one all those things. Then room latent heat, I am just writing the formula first, then I will go for the calculation. Room latent heat, which will be equal to, now we'll see what are the factors come under. So for room latent heat, this won't come, solar heat gain through glass won't come, equipment load, that won't come. Yes, infiltration load, yes, it will come. Okay, so I'll write infiltration latent load, infiltration latent heat, plus then obviously occupants latent heat. Yes, I will write the occupants latent heat, plus the next one product sensible, it's a sensible, fine. So that's it. I'll have the infiltration latent heat and occupants latent heat, that's it. Okay, nothing else will come under the latent heat, fine. Okay, now we will just go on calculating everything, okay, each and every parameter over here. So I'm finding the room sensible heat. Okay, room sensible heat. So first, solar heat gain through wall, roof and floor, so that is given directly. Okay, so heat flow through wall, roof, heat flow through wall, roof and floor, so that value they have given directly over here. It is 6.2 kilowatt. It is 6.2 kilowatt, fine. Next, solar heat gain through glass, solar heat through glass, okay, that is also given directly in the problem statement. It is 2 kilowatt. You take as it is, that is 2 kilowatt. Then equipment load also directly given, 2.9 kilowatt, fine. So you take as it is, equipment load 2 kilowatt. Okay, now in this statement lighting load is not given, so need not to consider. If it is given, you should consider that lighting load, and that will fall under the sensible heat only. Next is infiltration load. Okay, fine. So we'll go for the next one is the infiltration load. Now here if you observe carefully, for infiltration they have given the 400 meter cube per hour. This is not the kilowatt what is in the load. So we are supposed to find out this infiltration load in terms of kilowatt. Okay, so I will tell you how to do it. Okay, so now what I will do for this, we are supposed to go to the psychrometric chart, but before going to this infiltration load, first we will see what is the total sensibility due to occupants. Okay, so in this formula what I will do, we can write this at the last, fine. So I am just erasing this first, just a minute, it's okay. I will first write down the occupant sensible load, that we can calculate directly. So then I can write the infiltration. So occupants sensible heat, which is equal to, now see in this statement what is given, total number of occupants are 50, however the sensible heat per person is 58. So by mistake, many of you can, what you'll do, you'll take 58 directly, you can add 58 watt is given, you convert that 58 watt into kilowatt and you can use this value directly, but it is not the correct answer. What you're supposed to do, it is the heat per person given. So if I want to get the total sensible heat for the occupants, I need to multiply this particular per person heat in by the number of occupants. Okay, so if I want to have, it's a 58 per person, so the occupant sensible heat will be number of occupants into sensible heat per person. That is what you supposed to calculate. So number of occupants are 50 into 58. Okay, this much of watt heat will be added over there. Okay, so you do the calculation and you'll get the answer. So it is 58 into 50. This is 2900 watt. 2900 watt. Convert this 2900 watt to kilowatt. So it is 2.9 kilowatt. This is 2.9 kilowatt. Fine. Now we will go for the infiltration sensible load, because that's the last parameter, infiltration sensible heat. So if you see, I have considered this sensible heat through wall, roof and floor, solar heat through the glass, equipment load and occupant load. Okay, product load also you can directly write down, which is given directly. So product load is, in the statement is given 0.2 kilowatt. Okay, so you directly write it's a 0.2 kilowatt. So we are now going to find out what is the infiltration sensibility. So that is the only remaining. I will go for it. Okay, so product load is also considered. Fine. So here I will write infiltration load. Infiltration load. Okay, so to get the infiltration load, I need to make use of the psychrometric chart. So what is infiltration? It is the non-air conditioned air or the atmospheric air is directly getting added to the room air. Okay, and because of that air, whatever infiltration or whatever heat is added, that heat is nothing but the infiltration load. Okay, so I am writing infiltration load, it's a sensible heat. Okay, fine. So first we'll go to the psychrometric chart. So here the outside conditions are given 35 CDBT and 27 CWBT. So it's 26. Here somewhere you'll get the 27. So this is the point number 1. And 27 CDBT and 55% RH is nothing but the inside condition given. Okay, so this is the point number 2. Okay, now this particular line 1 to 2 is connected over here. Fine. Now we know that the outside air is directly added to the room air. Okay, so the outside air is at point number 1 or the state number 1, which is added to the room which is at the state number 2. So between this 1 to 2, what amount of sensible heat is added and what amount of latent heat is added, that is nothing but the infiltration sensible heat and infiltration latent heat. Fine. Now to get the sensible heat between 1 to 2, what I need to do, I will draw one vertical line over here from point number 1. Okay, I'll mark something like this, and I will have one horizontal line from point 2 over here, something like this. Wherever these two lines will intersect, I'll mark the point A. Now the sensible heat, we know that the sensible heat, the moisture content will remain same, however temperature changes. So from 2 to A is nothing but the moisture remains constant and the temperature is changing from point 2 to point A. So this is nothing but the sensible heat. Whereas this from point number 1 to point A, the dBT remains the same or the temperature remains same, however moisture content is changing over here. So from point 1 to point A, the moisture has been removed. Okay, so this is nothing but the latent heat. Now this sensible heat from 2 to A or A to 2, whatever it is nothing but the sensible heat due to infiltration. Whereas the from point 1 to A, where the moisture content is changed, so that is nothing but the infiltration latent heat. Okay, because infiltration air is coming from point number 1 and added to the point number 2. Okay, outside condition to the inside condition directly. So because of this particular 1 to 2, what is sensible heat added, that is this A to 2, and what is latent heat is added, that is 1 to A. Okay, that is what we are supposed to calculate. Now with respect to the point number 1, 2 and A, I will note down the enthalpies. So at point 1, the enthalpy is about 85. Point number 2, it is about 57, 58. Okay, it is about 58. Whereas with respect to point A, it is about 65, 66, 67, 68. About it is 67. It is about 67. Fine. So we will note down those things first of all. So I will have the enthalpy H1 as 85, H2 is 58, and HA is about 67. Okay. So these things we have found out from the psychrometric chart. Now what will be the sensible heat? Now if I want to write down the formula for sensible heat, it is obviously the enthalpy difference. Okay, it is nothing but the enthalpy difference. So what enthalpy difference I should consider? HA minus H2, that is the thing but the sensible heat from point 2 to A. So it is HA minus H2. However, I need to get this particular sensible heat, okay, in the kilowatt. If you see the unit of this particular sensible heat, it will be kilojoule per kg. It will be kilojoule per kg. So I'll have the unit as kilojoule per kg. And if I want to get this particular answer in kilowatt, I need to multiply this by kg per second, so that this kg get cancelled and kilojoule per second is nothing but the kilowatt. So what this term is kg per second, that is nothing but the mass of air. So what is the mass of air? This is nothing but the mass of infiltration air, the mass of infiltration air. But in the statement we have not got the mass of infiltration air. Okay, however they have given us the volume flow rate of infiltration air. So that is 400 meter cube per hour is nothing but the volume flow rate of infiltration air they have given. Okay, so if I want to write, so this will be in volume of infiltration air is 400 meter cube per hour. Okay, you convert this 400 meter cube per hour first to meter cube per second. Okay, because finally I am going to use all the values in kilowatt. So it is 400 divided by 3600. Okay, that is hour to second conversion. You need to multiply it by 3600 to that hour value. So 4400 divided by 3600, it is about 0.11 meter cube per second. So this is what the volume. This is the volume flow rate, but I didn't get the mass flow rate. I want to have the mass flow rate of infiltration air. And to get the mass flow rate of infiltration air, I can use the relation of mass of infiltration air is equal to volume of infiltration air about divided by specific volume of infiltration air. Okay. Now the value of the specific volume. Now if you see the units, the unit of this will be meter cube per second, and the specific volume unit is meter cube per kg. Meter cube per kg. So meter cube cancel. Finally, we'll have the kg per second. So this is nothing but the mass of infiltration air which is I require over here. So this value of specific volume of infiltrated air, this value we can get it from the psychrometric chart. We can get it from the psychrometric chart. So if you see over here, these lines, these slant dark lines are for the specific volume. You see the unit over here, it is 0.9 meter cube per kg, 0.88 meter cube per kg. So these are nothing but the specific volume lines. Okay. So with respect to the inlet condition of infiltrated air, so inlet condition for the infiltrated air is point number 1. Okay, that is the inlet condition of infiltrated air. So with respect to point number 1, whatever is the specific volume, consider that specific volume to get the mass. So here that exactly point is matching on the 0.9 meter cube per kg of air. So in this case, specific volume for infiltrated air is about 0.9 meter cube per kg. Now you can get the mass of infiltrated air because you know the volume flow rate, which is nothing but the 0.11 meter cube per second, and also you know the what is specific volume at the infiltrated air at point number 1, that is 0.9. So I'll be having the mass of infiltrated air which is equal to 0.11, that is the volume flow rate, divided by 0.9. Okay, so the answer will be, you just divide this particular 0.11 by 0.9. So this is about 0.123. Okay, it is 0.123 kg per second. So this is the mass of infiltrated air. Now once you get the mass of infiltrated air, you can easily find out what is the sensible heat, because in this case HA, H2 both are known to you. Mass of infiltrated air you have calculated over here. So hence I can calculate the sensible heat due to infiltration, which is equal to mass is 0.123, mass of infiltrated, that is this formula I am using, that is mass of infiltrated air is 0.123 into the enthalpy difference HA is 67 minus H2 is nothing but the 58. Okay, so this is what the answer you will get, and the unit of this answer will be in kilowatt, because this is in kg per second, this is nothing but the kilojoule per kg. So this answer, finally this answer is in kilowatt. So fine, you can have the multiplication over here. So 0.1123 into we'll have 67 minus 58, that is 1.11. The answer is 1.11 kilowatt. This is the sensible heat due to infiltration. Fine. So now we have got all the values of which are contributing to the sensible heat. I can finally find out what is the room sensible heat. So this also we have calculated. So I'll just go on putting the values to get the room sensible heat. So room sensible heat is equal to, I'll just go on putting the values. So solar heat gain through wall, roof and floor, it is 6.2. Fine, I will write 6.2. Then plus, then we'll have the solar heat gain through glass is 2 kilowatt. Solar heat gain through glass is 2 kilowatt plus, sorry, then you have the, so this we also consider. Then equipment load is about 2 kilowatt. Fine, you'll be writing the 2 kilowatt plus you will have is it 2 kilowatt only? 2 kilowatt. Equipment load is 2.9 kilowatt. Equipment load is this is 2.9 kilowatt. Fine. So here I need to make a change. It's 2.9 kilowatt. Okay. Then what is that infiltration sensible heat? Just now we have calculated sensible heat due to infiltration, that is this value is 1.11 plus you will have what next is occupant's sensible heat. So occupant sensible heat we have calculated, it is 2.9 kilowatt. Okay, this is the occupant sensible heat. 50 into 58, you have got this 2.9 kilowatt. Write down that also, 1.11 plus 2.9 kilowatt plus next is product load. Finally the product load, and the product load is given as 0.2 kilowatt. Correct na? Yes, it is 0.2 kilowatt. Fine, so we'll add this 0.2 kilowatt. Okay, so all these things will be adding one by one. Okay, so here we'll have 6.2 plus 2 plus 2.9 plus 1.11 plus 2.9 plus 0.2. Okay, 6.2 to 2.911 2.9 0.2. Okay, it is coming around to be 15.31 kilowatt. 15.31 kilowatt, that is the room sensible heat you have got. Okay, now you will find the room latent heat. Okay, now you will find the room latent heat. Now this room latent heat already we have seen, that is equal to infiltration latent heat plus occupant latent heat. Fine. So first I will find out the occupants latent heat, which is equal to, again, the number of occupants into latent heat per person or per occupant, anything you can do. Okay, so number of occupants are 50 into the per occupant latent heat per person. So this one is nothing but 44 watt. Fine, you write down 44. 50 into 44, find out this particular answer, convert that answer, the answer will be in watt, convert that to kilowatt. 50 into 44, 2200 watt. So it is 2200 watt, okay, which is nothing but 2.9, sorry, 2.2 watt. So it is occupant latent heat, occupant latent heat. And next is infiltration latent heat, okay. See here, so occupant latent heat we have calculated, nothing else is there after this, and infiltration now we are calculating infiltration latent heat. So again we'll go back to the psychrometric chart. So what is the latent heat over here? That is this 1 to A is nothing but the latent heat. So if I want to write down the formula, it will be H1 minus HA. So this is the enthalpy difference. Obviously, as like your sensible heat, you are supposed to multiply it by mass of infiltrated air. Now already you have the mass of infiltrated air calculated. No need to do the same thing again. Okay, just put the values. It is 0.123 into H1 is 85 minus HA is 67. Okay, so you just do this particular calculation. So 0.123 0.123 into 85 minus 67. Okay, so it is 2.214. It is 2.214 kilowatt. This is the kilowatt because this is in kilojoule per kg multiplied by kg per second. So kg get cancelled. Finally, we'll have kilojoule per second, which is nothing but the kilowatt. So finally, what will be the total room latent heat then? That is addition of this occupant latent heat and the infiltration latent heat. So it is 2.2 plus 2.214. Okay, 2.2 plus 2.214, it is 4.414 kilowatt. It is 4.414 kilowatt. So you have got the room sensible heat, you have got the room sensible heat as well as room latent heat. Now you can calculate the RSHF. Okay, so here I'll calculate the RSHF, which is equal to RSH divided by RSH plus RLH. Okay, so RSH, okay, you see RSH is what value we have got for room sensible, it is 15.31 plus 4.414, 15.31 divided by 15.31 plus 4.414. Okay, so this is what the room sensibility factor you will get. Okay, so we'll do the calculation. 15.31 divided by 15.31 plus 4.414, it is 0.776. okay, it is 0.776, so I am considering it is 0.78. so RSHF you have got as 0.78. okay, now the next problem remains the same which we have solved previously. Okay, we'll follow the procedure again. Now once you get the RSHF, this is the first answer you have got. Now you can get what is the supply air condition directly. Fine, so go back to the psychrometric chart. Now to get the once you get the RSHF, you can plot the RSHF line. So 0.78 over here you will have the RSHF. This is the RSHF. Connect this RSHF with the alignment circle, something like this. The first step, okay, to this particular line, this is known to be the baseline. Okay, this is the baseline. To this line, draw one parallel line from the point number 2, that is the room design condition, something like this. Okay, so this is the RSHF line, this is the RSHF line. Now one thing is sure, on the RSHF line you will find the supply air condition, you will find the supply air condition. Fine, so to get the supply air condition, either two values will be given, two or three values, they directly supply air condition will be given, or ADP is given, or bypass factor will be given. So in our case the ADP is given over here, ADP is given over here. Fine, so to get that, now obviously we need to draw the schematic of this particular thing, correct na? So by looking at this particular diagram, I need to draw the schematic. So 80% is written here. So for suppose that you have the room over here, this is the room, which is to be cooled, which is maintained at the state number 2. We know that always by default I will consider the room condition as state number 2. This is the cooling coil. Okay, so and there is the blower over here. From blower the air will be supplied to the room. Okay, from room the air will be taken back. As nothing is mentioned about where the mixing is done, by default I will consider the mixing is before the cooling coil. Okay, so this is the cooling coil, this is the cooling coil, this is the blower. So before the cooling coil I am considering the mixing. This is the point number 2. Obviously I am taking the fresh air, outside air, that is at the point number 1, or the fresh air. So there will be the mixing between 1 and 2, and the mixed condition will be point number 3. That air will be passing over the cooling coil. Obviously because of the heat transfer between the air and refrigerant, the state of this particular point 3 will change, and it will be the state number 4. At the state number 4, air will be going to the blower, and from blower it will be supplied to the room. So the supply point of the air will be the point number 4 only, whereas the return will be taken at point number 2. Okay, so the schematic is something like this. So in this case I need to see, obviously the ADP is with respect to the cooling coil. Ideally the cooling has to be done from point number 3 to apparatus dew point temperature of the coil, or the surface temperature of the coil, that is the ADP. However, because of the losses that or the bypass factor, the cooling is not up to the apparatus dew point temperature. It will be up to the point number 4. Okay, because of the losses. So here I need to consider that particular thing over here. Okay, so first I will find out what is the mixing condition over here. So now I know that to get the mixing condition I am using the formula M1 by M2 is equal to H3 minus H2 divided by H1 minus H3. This is the formula I will be using, which I have got from the mixing of two air streams. M1 is nothing but the 20% of air, M2 is 80% of air. H3 value we don't know, that is the only we are supposed to calculate. H2 value we already got it, so H2 value is 58 and H1 is 85. So it is 58 divided by 85 minus H3. Solve this particular thing, you can get the what you can say the H3 value. So 0.8 into H3 minus 58, which is equal to 0.2 into 85 minus H3. Okay, so when we do the calculation, so it is again 0.8 H3, it is 0.8 H3 minus 0.8 into 58. Already we have this value, but still again we will do it. 0.8 into 58 is nothing but the 46.4. It is 46.4, which is equal to 0.2 into 85. 0.2 into 85, it is 17. Okay, 17 minus 0.2 H3. Okay, I'll take the H3 term on one side, 0.8 H3 plus 0.2 H3, that is 1 H3, which is equal to 17 plus 46.4. So H3 is equal to finally 17 plus 46, 63.4. 63.4. So somewhere over here at 63.4 I will have the H3. So 61, 62, 63, 63.4. So somewhere over here I am having that particular enthalpy. So with respect to this I will draw one line which is parallel to the WBT line. Okay, now it is coming down. Fine. Okay, this is the line I have drawn. Now I know that the mixing is between 1 and 2. Mixing is between 1 and 2. So obviously the mixing point, that is the point number 3, definitely will be lying on the mixed condition over here. Sorry, on the line 1, 2. So this is nothing but the point number 3. This is nothing but the mixed condition point number 3. Now I can get the supplier condition by using the data given over here. So to get the supplier condition, the data given over here is the apparatus dew point temperature. Apparatus dew point temperature. Now as I said, the ideally cooling has to be done from point number 3, that is mixed point, up to the surface temperature of coil, that is nothing but the apparatus dew point temperature of the coil. But because of the losses it is happening up to point number 4. So I will be connecting the point number 3 with the apparatus dew point temperature over here. So that is the cooling process, ideal process. Okay, so from point number 3 up to the ADP of 8. So this is 10, 9, 8. So here is the ADP given. This is the ADP. Okay, so up to ADP I can have the cooling over here, something like this you will have the line. Okay, something like this will have the line. I have considered ADP on the lower side, so that's why you are getting this particular line. So wherever this line, just a minute, I will just erase this particular line, single line I will draw so that it will be better for you. Okay, fine, I will draw the line. So you are going to use the scale, so when you are using the scale, you will get the things correctly. Something like this I'm having the line. So wherever this line is intersecting to the RSHF line, that is nothing but your supply air point number 4. We know that this line 32 ADP is nothing but what is the GSHF line. So intersection of GSHF line and the RSHF line is nothing but the supplier condition. Okay, so this is the supplier condition. So with respect to supplier condition, you can find out the various points. So the temperature is about 21 degrees Celsius, dry bulb temperature. Wet bulb temperature is about 17.5 degrees Celsius. Okay, so from the psychrometric chart, you can draw these lines. So say the answers for supply air condition, so it is dBT at 0.4, which is nothing but 21 degrees Celsius. WBT at 0.4 is about 17.5 degrees Celsius. RH we will see, W we will see what are the values are there, as well as the enthalpy at point number 4, which is required. So here I am having the RH is about this is 70%, about 72%, and W value is about 0.0 near to 0.0012. So it is, so W will be RH is 72.5% and it is 0.0108. okay, so that is 118 rather 118. okay, and the enthalpy for this is for point number 4, the enthalpy is about 50. It is 50. okay, obviously I'll draw one line parallel to the WPT line. Wherever it is intersecting to this enthalpy scale, I'll get the enthalpies here, somewhere here. I'll just show you the line, something like this. So this is nothing but the H4, which is nothing but the enthalpy, and the answer is about 50. okay, assume that it is 50 kilojoule per kg Kelvin, kg. So these are nothing but the supplier condition. The next one, what is the asked next one, that is the bypass factor. Okay, now bypass factor, obviously you can get it from the psychrometric chart only. So what will be the bypass factor over here? Bypass factor will be the length. We know that it is obviously the cooling has to be done from 3 to ADP ideally, but because of the losses, the loss is nothing but this. Okay, because of this loss, the cooling is done up to the point number 4. So the length ADP to 4 is the bypass factor. ADP to 4 is the bypass factor. So it is length ADP to 0.4 divided by total length. Cooling total length is ADP 2.3. okay, so you take the length and from that you can get the bypass factor. okay, whatever answer you get, you can write down that. So this diagram is not with the scale, so I am not what you can say, I'm not giving you the answer. You can get the answer from your side. I just tell you the procedure, that is length ADP to 4 divided by length ADP to 3. We will get the bypass factor. Fine. Now I want to get the cooling coil capacity. okay, so cooling coil capacity. So we know that now across the cooling coil, whatever the enthalpy difference is there, so that enthalpy is for the cooling coil capacity. So if I want to write the formula for cooling coil capacity, so across coil, what are the points? That is point 3 and point 4. So between 3 and 4 only the cooling is happening. okay, and for that only whatever the capacity is there, that we should write down. So we know that we already have seen various times the formula. So I need to multiply it is the mass of dehumidified air, or whatever mass is flowing over the cooling coil. So it is the mass of dehumidified air into H3 minus H4. That is the cooling coil capacity. Fine, but I don't have the value of MD. The mass of dehumidified air is not with me. H3, H4 I have. So to get the mass of dehumidified air, I need to make use of the total heat generated inside the room. Okay, so total heat generated in the room which is equal to the total heat absorbed by the dehumidified air. Okay, total heat absorbed by dehumidified air in the room, dehumidified air in a room. Okay, so now what is the total heat generated inside the room? That is the room sensible heat plus room latent heat, that we know, which is equal to what is the total heat absorbed by the air in the room. So if you see the schematic, you'll come to know. Now I am supplying the dehumidified air, that is MD mass, I am supplying it to the room, and when that air is coming into the room, that will take the heat from the room, so whatever enthalpy difference across the room into the mass supplied over there, that is nothing but the total heat removed by the air. Okay, so here H2 and H4 are the enthalpy difference across the room. So my formula to get this, what you can say, the total heat absorbed by the room is mass of dehumidified air into H2 minus H4. So we know that the total room sensibility is about 15.31 something. That answer was yes, 15.31. This is the total room sensible heat, and room latent is 4.414. So it is 15.31 plus 4.414 is equal to MD into H2. H2 value is already we have, it is 58, and H4 is 50. So it is 58 minus 50. So that from that I can get the mass of dehumidified air. So you can calculate that mass. It is 15.31 plus 4.414 divided by 58 minus 50. So I'm getting mass of dehumidified air as 2.46. Now what is the unit of this? So this is in kilowatt. Okay, so obviously this answer will be in kg per second. This is, sorry, kilojoule per second. This is also value of enthalpy is kilojoule per kg. Finally answer I will get is kg per second. So this is the mass which is across the are supplied to the room dehumidified air. Now I can put this answer over here in the cooling coil capacity formula. So CC capacity, cooling coil capacity is equal to 2.46 into the enthalpy difference across the cooling coil, H3 minus H4. So value for H3 is where we have got H3. H3, fine. H3 we will, yes, here we have got that value. H3 is 63.4. So here it is 63.4. That is the H3, and H4 is 50. Okay, so 63.4 minus 50. Okay, H3 H2 I need H2. H2 is 58 minus, sorry, H3 minus H4, this formula correct, H3 minus H4. So H3 is 63.4 minus H4 is 50. I can get the cooling coil capacity. So we'll just find out the cooling coil capacity now. That is 63.4 minus 50 into 2.46 is what the mass flow rate. So it is 32.96 kilowatt. So this answer is in kilowatt. Okay, convert this kilowatt into tons of refrigeration by dividing it by 3.5. So we know that 1 TR is equal to 3.5 kilowatt. Use this relation to get. So I'll get the answer as 9.41 tons of refrigeration. So this is the cooling coil capacity. Okay, so this is nothing but the cooling coil capacity of the room. So if I want to maintain the room at 27 C and 55% RH, I need to put the coil of 9.4 tons of refrigeration. Okay, so this is how you will be solving the numerical based on the cooling load estimation. So in case of cooling load estimation, never ever directly room sensibility and latent heat will be given. You supposed to calculate the room sensibility and latent heat by using these formulas. Fine. So in some cases it won't happen like that. All the factors what are given over here, they will be giving into the numerical statement.
might be you'll have one or two factors, maybe only infiltration load is given, latent or the occupant load is given, occupant and infiltration given likewise. Okay, so whatever given is there, only consider that and you do the calculation. Fine. So but this is the procedure you should follow to get the things. Now if instead of this ADP, if the bypass factor is given, then what you would have done, that H3 you have got already. Okay, H3 you have got, so you will be adjusting the scale over here such that the length from saturation curve to the RSHF line divided by the length from saturation curve to the point number 3 has to be equal to the bypass factor. So that trial error method will be using, and you will get the point number 4 over here. Okay, so that is what the variety of problem you can get. Fine. So thank you. So that's it. If you are having any doubt, you can write down into the comment. I'll try to solve those problems or the issues or the doubts you have. Fine. Thank you.